about my talk. It is somewhat related to the talks earlier today, especially the previous talk. It is quite different. I will talk about condensation and superfluidity in magnetic insulators driven out of equilibrium. I will try to convey some really basic pedestrian ideas which we find already interesting at a very elementary level. So since this is the only talk of the kind, I will focus on very simple basic things just to give you a flavor of what we're interested in. These are the people who's done most of the work, my former PhD student Scott Bender, my collaborators at Utrecht, my postdoc at UCLA, and there will be two experimental works that I will touch upon, one by Ilya Krivorotov and another by Amir Yakov's group. A quick disclaimer, there will be at least two things I will not talk about, which are closely related, just in the interest of time. I will skip those. One is related issues in superfluid helium-3. That work is pioneering, interesting, and foundational. In this talk, I will, however, focus on strictly solid-state systems. So I will drive my system by solid-state means, by electrical current, by heat currents, and I will look at solid-state transport manifestations. All right, so that's a tale of two types of spin flows. Incoherent type of spin flow that could be driven by thermal gradients, so the gradients in the chemical potential, and a superfluid-like spin flow that is driven by the gradients in the coherent phase. So it's just a little advertisement, but of course I will elaborate on what exactly I mean. So 3 parts to my talk, and I would like to sort of emphasize these keywords that I will elaborate on during my talk. I will describe two fluid dynamics transport in magnetic insulators, much in the spirit of the two fluid description presented in the last talk. So we'll have a coherent fluid and incoherent fluid. They're going to be coupled together, and the coupling is crucial because the incoherent fluid will be pumping the coherent fluid, or feeding the coherent fluid, will be the source of the coherent condensate. And in turn, standard solid-state means like thermal gradients, voltages applied to the system will directly couple to the incoherent fluid. So that's kind of the essential idea. So that's a two-fluid view on magnetic dynamics with a specific focus on transport in magnetic insulators. And then the two, once I introduce the subject, give you sort of outline some basic formalism, I would like to describe two experiments which we believe address the physics that we're after. First experiment in the Yakovic group on a detection of magnon chemical potential. So that's a sort of new aspect that is really important for understanding, a central aspect for understanding the fluid dynamics. So that's the first experiment that directly detected, measured magnon chemical potential. I will tell you how that worked out, just to give you, just to basically provide really the foundation for this formalism, just basically to show that it does make sense. And more so forward-looking experiment that is more relevant to this conference on thermoelectrically pumped instabilities of magnetic insulators, which we can understand as magnon condensation, and we'll distinguish two regimes of magnon condensation. One is more like lasing, the other is more like BEC. I'll try to explain what I mean by that. All right, so the bird's eye view of the kind of system we're interested in. I will focus on sort of a toy model, but practical toy model that illustrates much of the physics. Namely, we will consider a simple ferromagnet that can undergo some coherent dynamics in time. Of course, it's out of equilibrium, so in some steady state, we may have a situation in which the order parameter precesses. and I want to establish that steady state in a fashion that precession is spontaneous. So I'm not going to drive it by RF fields. This precession will appear spontaneously out of some thermoelectric pumping of the system. Of course, such coherent dynamics is intricately coupled with the incoherent dynamics that could be understood as a gas of thermal magnons described by some temperature and a non-zero chemical potential. So the fact that the incoherent magnon gases can be driven far out of equilibrium in terms of not just effective temperature but the chemical potential, that is sort of the novelty, I would say, of the materials that we're interested in our field, and the fact that the materials with low enough spin orbit relaxation, long enough magnon lifetimes exist that we can speak of non-zero chemical potential. That basically is the foundation of everything I'm going to tell you today. And naturally, then we have to ask, well, how do we measure this chemical potential? And I will address that question as well. In contrast to the incoherent magnons, the incoherent, in the environment, which in this minimal description is just phononic bath, for my purposes, I will describe it as featureless. So in principle, that's another thing to experimentally couple to, and people have various ideas on doing that, but in my talk, I will focus on this side of the story. I will suppose that phonons behave as a featureless environment that sets, thermalizing environment that sets a temperature. But it's still a useful part of the story because I can couple to this environment and apply heat currents and use that to drive magnetic system out of equilibrium. Okay, so the first experiment that illustrated that a magnetic insulating system can be used for long-range transmission of spin signals was performed at the group of Bart van Wees in Groningen. So this is a cartoon, a schematic of the experiment. It's based on a transport of magnons, diffusive transport of magnons through YIG. YIG is a very simple sort of fruit fly of magnetic insulators. So the band structure is complicated, the crystal structure is complicated. The material is really nice, well characterized ferromagnetic insulator. So the fact that the Gilbert damping, the damping of magnetic dynamics is low, and the lifetime of magnons is long, allows to design this kind of experiments in which you use magnetic contacts that inject spin via the spin Hall effect. That spin propagates over long distances experimentally at room temperature up to tens of microns or so, and can be detected non-locally by another normal metal contact that converts the spin current at this interface into voltage by the inverse spin Hall effect. Okay, so I'm not going to go into the microscopic details, but just keep that in mind that these days, in this kind of lateral geometry, metals are routinely used for injecting spin by the spin Hall effect and detecting spin current by the inverse spin Hall effect. The key here is that we have long range, in this experiment, we have long range transport of magnons. Now, the question that I want to ask in this talk is, if we drive this or other type of similar systems based on similar, perhaps based on similar materials, far enough out of equilibrium, whether we can achieve regimes of condensation of magnons and in relation to that superfluid transport phenomena. So to go beyond diffusive character of transport. Yeah.
So you say you inject spins, so you inject them like in the entire Brillouin zone, or you inject them at some momentum?
Sure. There will be basically the simple answer. You will inject them over the entire thermal distribution of your thermal magnon gas. So more or less over the entire Brillouin zone. So at room temperature, more or less. I mean, the band structure is very complicated. There are actually 21 magnon bands. The details are complicated. There are matrix elements that may depend on the bands. But essentially, yeah, that's kind of one property which is different from some kind of microwave parametric excitation, is that it's really terahertz magnons which are responsible for the injection, and they basically probe more or less most of the half of the brilliance zone according to the thermal distribution. And because of that, they internally equilibrate very quickly on very fast sub-picosecond time scales to a common temperature potential, chemical potential. And then those could propagate through the system in some diffusive or superfluid fashion if the magnons are pumped hard enough to undergo condensation. No, you're referring to magnons in the insulator, right? Yeah. All right. So to understand now to develop some basic understanding of what happens in the magnetic insulator. So it looks okay. At the boundaries, you have some injection, some detection. Let's now focus on what happens in the insulator in terms of local dynamics. Once we understand the local dynamics, and we'll discuss propagation of spin signals in the presence of some inhomogeneities. Specifically, I want to contrast ultimately the diffusive and a superfluid type of propagation of spin signals. So locally, that's a cartoon of what you could expect. There's an order parameter. That order parameter moves in response to some external fields, or self-consistently in response to some torques exerted on this order parameter by the thermal magnons. Those torques have to be, in linear response, will have to be due to the chemical potential of magnons. So if magnons have, whatever temperature magnons have, of course, that should not exert torque on the collective dynamics. Otherwise, you would have some coherent dynamics emerging spontaneously out of equilibrium. That's nonsense. But chemical potential, that is another parameter that parameterizes the non-equilibrium state of pumped thermal cloud. Chemical potential, in principle, depending on this magnetic, on the symmetries of the crystal, magnetic interactions, may exert a torque, and we'll show that will be actually key. Reciprocal to that, the order parameter dynamics will pump the thermal cloud. So there will be some source terms in the diffusive description of the transport of the thermal cloud, which will be proportional at the leading order to the precessional frequency of the order parameter dynamics. So this kind of physics you could expect on very general principles. Once the thermal cloud is driven out of equilibrium, it should play out in ferromagnet, antiferromagnet, spin glasses, any magnetic ordered or disordered system. We'll focus, of course, on the simplest case, which is the ferromagnetic. Just to give, I have two slides, kind of technical slides. One on just to give you a flavor of the microscopics that based on which you could sort of work everything out, and then phenomenology that kind of folds everything into just one phonological parameter that describes both torque and the pumping. Is just one parameter because of Anzaga reciprocity. There could be more parameters depending on more complicated structural symmetries, but focusing on the simplest case of the axially symmetric system. This axis could be easy axis or the hard axis for the ferromagnet. The system axially symmetric, so we have conservation of spin, correspondingly conservation of magnon number, either condensed or thermal along this axis. So for the simple case of axially symmetric dynamics, will be just one parameter. Ultimately, phenomenologically, that describes everything. Microscopically, this is a sketch of what's really happening. You could bosonize magnetic dynamic, transverse magnetic dynamics according to Holstein-Primakov transformation, separate the bosonic field by the Bogoliubov decomposition into the coherent piece and the piece responsible for thermal and quantum fluctuations on top of some coherently processing field. This coherent piece, you could define both the phase and the number of condensed magnons, or of course they're in one-to-one correspondence. The incoherent piece defines the number of magnons in the thermal cloud. And then if you develop, these are going to be the thermodynamic quantities, Nc, phi, and tilde the density of incoherent magnons. If you develop now some transport theory in terms of this quantity, you're going to get equations similar to the ones that you saw in the previous slide, like some kind of Gross-Petayevsky equation with some relaxation and some source terms and some diffusion theory for the thermal cloud. Question?
Yes. To use Host and Primakov, you need to fix the quantization axis.
The symmetry axis. So let me, for simplicity, suppose that this is, I'm expanding the theory with respect to magnetization pointing down. So then the condensate simply corresponds to the tilt of the order parameter. So the condensate density roughly corresponds to this component of the coherent magnetization, and the thermal cloud corresponds to sort of the thermal demagnetization of the order parameter. But everything expanded with respect to small angle fluctuations, coherent and incoherent, relative to the z-axis. Okay, and so in this fashion, both coherent and incoherent, everything is treated sort of on equal footing. Everything derived from the same kind of microscopic Hamiltonian. The key piece in constructing the coupling between the cloud and the condensate is the magnon-magnon interaction due to this anisotropy, either easy axis or easy plane. K parameterizes the strength of that anisotropy depending on the sign, it's easy axis or hard axis. Substituting this decomposition into the magnon-magnon interaction, and expanding it out in terms of the coherent and incoherent pieces, we get these types of processes which are responsible for evaporation of the condensate into the thermal cloud, or the reciprocal process of condensation of the thermal cloud if that cloud is oversaturated. If somehow the chemical potential of the cloud is pumped by some means, specifically pumped above the gap of the spectrum, then the thermal cloud will spontaneously condense and sort of tilt magnetization out of equilibrium, inducing real-time coherent dynamics. Okay? Now, phenomenologically, this could all be folded, and at the end of the day, that's all pretty much you need to start comparing to experiments. Could all be folded into two equations. This is essentially, this is now large angle dynamics version of what would be Gross-Pitievsky equation for small angle dynamics. So for small angle dynamics, we could fold everything into the Gross-Pitievsky equation. But for large angle, especially when this Holstein-Primakov transformation acquires large geometric factors beyond simple sort of low-order bosonization, then we should switch to the Landau-Lifshitz equation that describe precession of the order parameter in some effective magnetic field with a damping, and the key new element is provided by these two terms, Onzaga reciprocal terms. That's the torque on the coherent dynamics proportional to the chemical potential. So that is the torque that would establish a condensate in the first place. This is the kind of torque that would be responsible for condensation if you have means to pump the thermal cloud of magnons, namely raise the chemical potential. If the chemical potential is raised and becomes larger than the gap of the magnon spectrum, at least in the absence of Gilbert damping, that would lead to instability, and that instability is captured by the torque and the reciprocal pumping of the coherent dynamics into the thermal cloud, and in the presence of additional phonological damping due to magnon-phonon interaction, of course, that will raise the threshold for the instability, because then this torque will have to overcome both pumping and additional magnon-phonon relaxation. So at this level, all of the essential physics elements are captured. This is really quite general expression for the phonological torques pumping that add to the LLG equation for the directional order parameter dynamics of the ferromagnet. And in general, you have to solve this in conjunction with a transport equation, some simplest case, some diffusion equation for the propagation of the thermal cloud density and tilde. So that would be a diffusion equation, also some relaxation term proportional to the chemical potential. And reciprocal to these two guys, there's a torque term that you could just lump together with the dissipation and pumping. So really the two, also this pumping could be lumped with Gilbert damping. So the two really new aspects that you would have to add on the experimental list, let's say, would have to add to understand really what's happening, is the torque on the coherent dynamics by the chemical potential of pumped thermal cloud, and reciprocally the pumping of the thermal cloud by the coherent dynamics. And those have to be solved consistently. Of course, the remaining question is, well, how do we induce this mu, the chemical potential? How do we shift it away from the equilibrium to start with in order to trigger this dynamics? So that I will describe in the next few slides. But that this at least phenomenologically, once the dust settles and we understand everything, these kinds of equations describe all of the physics that I've advertised, all of the physics that we're after. Specifically, in the next few slides, I will address the problem of the formation of the heat-driven magnon condensates and the ensuing to fluid hydrodynamics. So I will use externally applied heat current to shift chemical potential away from equilibrium. So it's some kind of analog of a thermoelectric effect in insulators, applying heat current, shifting chemical potential of your quasi-particle. And then ultimately that leads to two fluid hydrodynamics of spin and heat, like the two fluid, with some similarity to fluid hydrodynamics in a superfluid helium-4 or 3. And I will just briefly touch upon this issue. But okay, let me focus on this business, namely cranking up mu by applying heat current through the system. Question.
So introduce this model phenomenologically. Can you start from something like?
No, that's basically the microscopics.
Can you start from like Heisenberg?
Yeah. Right. So this is basically Heisenberg Hamiltonian plus anisotropy. I have to add anisotropy, otherwise, just within the SU2 symmetric Heisenberg Hamiltonian, I will not couple coherent dynamics to the cloud.
Obviously, that you can write spin dynamics. Examples with a lot of momentum dependence in matrix element.
Of course, yeah. But we have a conservation law, which is the total spin along the z-axis.
It's not enough to write hydrodynamics.
No, I'm not saying that it's enough to write hydrodynamics, but the hydrodynamics, so in this, along these lines, it kind of naturally emerges.
No, but maybe you have to solve a full Boltzmann equation for all momentum equations.
Sure. Yeah, what helps? What helps in practice, at least at elevated temperatures. But I'm interested here at really room temperatures. Many of the relevant experiments at room temperature. What really helps is that first of all we have very strong magnon-magnon equilibration that relaxes on timescales much faster than this interaction between the condensate and the cloud relaxes thermal cloud to the common chemical potential and temperature. So that means I don't really have to develop an intricate Boltzmann description of the thermal cloud.
But that you put in as an assumption, do you know?
Well, it follows from the Heisenberg Hamiltonian, let's say. You could estimate, there are no conservation laws essentially other than the spin along the z-axis. So you could estimate the rate of internal equilibration of the cloud, and that equilibrates the cloud to a common chemical potential that's different from zero because the spin is conserved. So the only way the spin can be relaxed in the thermal cloud is by exerting a torque on the condensate. So between the two subsystems, the spin is conserved. Yeah, question.
Your flood of the present condensate, is it possible to be the responsible system? Yeah. Is it only the T?
Yeah, absolutely. Yeah, I mean, again, if you work out, it will be proportional to the omega t, where omega, again, has to be self-consistently calculated. But it's just a precession. It's a classical precession of the transverse. That's the chemical potential of the condensate. Yeah, the chemical potential of a thermal cloud could be different. So the cloud and the condensate, they are out of equilibrium, but precisely the difference between the chemical potential of the condensate and the cloud, that's the source term that redistributes the angular momentum between the two. If the interaction parameter eta that describes this process is, if I just by hand send to infinity, then the condensate and the cloud will be locked to the common chemical potential. In general, they have different chemical potential. And for example, I could start with chemical potential of my cloud at 0. I can induce dynamics of the other parameter, whatever, by some RF field, by microwaves. It will take some time for the chemical potential then to build up to the level of the frequency of the coherent dynamics. And the way the chemical potential builds up is precisely described by these equations. All right, so in the remaining couple of minutes, Okay, let me now talk about, so this is we've constructed the theory, we have some basic microscopic phonological understanding. Let me now apply it to 2 experiments. I will have something to say about those experiments. I will also use the experimental data to actually extract this parameter eta that describes the pumping and the torque. So that's the experiment at the Amir-Jacobis group, in which they use same material, YIG, room temperature, with the gold strip line that drives coherent magnetic dynamics of YIG, coherent precession of YIG, just a standard FMR. That coherent precession of YIG pumps the thermal cloud, shifting the chemical potential. And the NV center here is used as a detector of the microwave radiation of the thermal magnets that is used to extract experimentally the value of the chemical potential. So the way it works, in a nutshell, you have a spectrum of magnets, you have some thermal fluctuations. You measure the transition rates between NV center spin states. Those transition, the T1 type of transition rates, energy relaxation rates, those energy relaxation rates, where the Fermi's golden rule, are directly proportional to the occupation number of magnets at the appropriate frequency. So by measuring this relaxation rate, you can measure the occupation number of magnets by measuring the occupation number of magnets at different energies using the classical limit of the Bose-Einstein distribution function, really Jeans distribution function. You could extract the chemical potential. So basically, inverting this equation and having this experimentally measured in equilibrium without drive and after with drive coherent dynamics at the FMR frequency, we can extract the chemical potential in terms of the ratio between the NV center relaxation rates without the drive and with AC drive. So the 2 take-home messages to take from this experiment without getting into the details of the data is that, first of all, so the system, the YIG magnetic film is driven as a function of the external field, as a function of the drive power. As the drive power goes up, the chemical potential of magnets that you extract saturates precisely at the FMR frequency given by the Kittel formulas. That's something that we know just from the magnetization, saturation magnetization of the film. So this is theoretically calculated Kittel formula for the frequency of the coherent FMR dynamics that is driven by the microwaves. And these dots are experimentally extracted values of the chemical potential from this formula without any fitting parameters. So it shows very convincingly that the language somehow makes sense. As with driving thermal cloud with coherent dynamics, initially the chemical potential of creeps up linearly and eventually saturates, for large enough drive, saturate at the value given by the FMR frequency. Another bit of the experimental data is by fitting now the linear slope of how chemical potential increases with the drive power, we can experimentally extract that single parameter eta that describes a coupling between the cloud and the condensate. And we can extract it from any of these data points. And it's nice that the curve, the theoretical curve in terms of one fitting parameter, follows qualitatively what experimentalists see as a function of the external magnetic field equation.
So mu going to 0 means that at the
equilibrium.
At the resonance we should choose quantization axis in the xy plane, right?
Say it again?
At the resonance, the quantization axis should be chosen in the xy plane, not along z. Is that correct?
I don't understand. So here there's external field which is applied just from the NV center point of view to optimize NV center detection, applied along the orientation of the NV center. It's just really a single NV center that is used for the detection here. So the magnetic field is applied out of plane. Magnetization is still out of plane. So you would do Holstein-Primakov with respect to the equilibrium orientation of your magnetization, which tilts out of plane as a function of the external field. That actually is what corresponds to this curve. But, okay. So, by the way, we're kind of eating into the discussion time, but I'm happy.
You just have real so the sign of the chemical potential does have to be significant.
Yeah, it could be positive or negative. Right. So, of course, naturally, if it's a ferromagnet, right? So there is a specific chirality of the coherent precession. So if If you tilt it, there's a chirality of precession. If you somehow by hand reverse that chirality, for example, if you drove not by RF field, just by some kind of spin torque externally, that would induce negative chemical potential. So it's a bit unphysical. So naturally, you induce positive chemical potential if you drive sort of with a natural chirality. Yeah. Okay, so now let me quickly touch upon the other piece in the final 2 minutes. So now this concerns the proposal to shift the chemical potential by applying thermal gradient to a magnetic film. We propose to apply thermal gradient vertical to the magnetic film with the intention to shift the chemical potential, initially in proportion to the magnitude of the heat flux, ultimately getting into the nonlinear regime when the chemical potential exceeds the gap of the Magnum spectrum, self-consistently and spontaneously creating the condensate. So this is condensate sort of turned on in the steady state, not in the pulse fashion, in the steady state, simply by sending heat current through a magnetic film sandwiched between two different metals. So one metal has to be hot, and there has to be a spin injector, namely that metal has to have strong spin-orbit interaction. So it will be acting as a reservoir for both heat and spin that could be driven by heat current into the system. The bottom substrate, that could be metal or an insulator, such as sapphire, should be a good heat conductor, but a bad spin sink. So this interface sends through heat current, just the heat current. This interface sends through heat current and spin current. As a result, spin is trapped in the film, and the critical value of driving, it's trapped, rises chemical potential, and at the critical value of driving, you undergo Bose-Einstein condensation. So that's, in the nutshell, what is happening. There are more details. You could also, in addition to this heat drive, which goes in our field under the name of the Spin-Seebeck effect, you could also apply electrical drive by sending electrical current tangentially to the interface at the top metal. So that injects spin by the spin Hall effect, the same spin Hall effect I mentioned in the second slide. So you could then look at the phase diagram of what happens to the driven magnetic system subject to this DC pumping, thermoelectric pumping, the Spin-Seebeck and spin Hall. And it's quite interesting. So we distinguish between, so the blue stands for the condensate, and we distinguish two regimes of condensation. Bose-Einstein condensation that is triggered by the thermal cloud, and the lasing or swaying spin wave lasing condensation that is triggered kind of more directly by the spin Hall effect by coupling electron hole paths in the metal directly to the coherent dynamics of the magnetic film. So sparing you of the details, let me just say that there are two experimental reports that we believe probed this phase diagram along sort of the BC trajectory, essentially sending primarily heat current through the system, as well along the what we call swaying lasing trajectory, sending mostly applying mostly spin Hall torque to the system. And that was performed. These are cartoons of the experiments: spin Hall geometry, Spin-Seebeck geometry. Similar heterostructures, platinum YIG with some featureless substrate, insulating substrate, but with a different setup of the contacts and the geometry of the structure, so that in one experiment, the heat current was dissipated away from YIG. So the torques were primarily of the spin Hall character, so we understand that as the sort of lasing regime of the condensation. And then in collaboration, this collaboration I was part of with my colleague at UC Irvine, the device was designed to focus heat current produced simply by Joule heating in platinum onto YIG, and then the Spin-Seebeck sort of thermally driven BEC type of condensation took over and lowered the overall threshold of the condensation. Experimentally, the onset of that condensation, or the appearance of the condensation, was detected by simply measuring microwaves, very coherent, very sharp microwaves detected at the contacts. So the same device is used, the two contacts are used for sending electrical current in, DC, steady electrical current, and then some critical value of that electrical current when YIG undergoes condensation. It processes via the magnetoresistance of the platinum YIG interface in the presence of the DC current that produces fluctuating coherent voltage that is measured between these two contacts. So we interpret this data of the microwave emission as the signature of the heat current condensation induced in YIG. You could develop these ideas towards coupled superfluid dynamics, for example, realizing the conveyor belt superfluid flows in which the normal and the superfluid components sort of naturally counterflow, the kind of physics that, of course, is well known in superfluids and superconductors. That's the physics that is responsible for the record high, basically thermodynamically infinite heat conductivity in superfluid helium, also for the vanishing thermal power in superconductors, and in our case, we have vanishing spin-Seebeck effect, again, as a signature of the spontaneous onset of the condensation. Thank you for your attention. I'm still within the time frame because of the questions, but yeah.